Hi, hello, welcome to section 4 of chapter 8. In this section, we are going to discuss topic called limiting reactant. And I would say this is one topic that chemists would enjoy and chemistry haters would pull their hair really well. But I got a plan. I think the plan would work. We are going to break it down and discuss it. So just raising the expectations that it is already a challenging topic. So I need your attention while you listen to this, right? So what is this limiting reactant is? Let's review what we discussed previously, right? In the previous section, we discussed that if you know the quantity of the one reactant, either in grams or moles, you can predict the quantity of another product in moles or grams, right? You could do that. What if you have started the chemical reaction with two reactants with the two different masses, and I ask you to predict the product either in moles or grams? Which one do you choose? Which one of these reactant masses would you choose? This is when it gets challenging. So just before you start doing what we did in the previous section, converting grams to moles and moles to moles and grams and call it a day, here you need to first identify which one of the given reactant masses are actually limiting reactant masses, which one is excess reactant masses, because only the limiting reactant would be responsible for how much of the maximum product a reaction can produce, because limiting reactant by definition is the one that used up in the chemical reaction first. So if you already used up one part of the necessary reactant, you cannot produce more of the product. So the maximum amount of product that you can produce is always dependent on your limiting reactant, the one that is available less. So no matter how much of the other reactant is present, it doesn't matter. You cannot complete the reaction more than your limiting reactant quantity. So whenever a question gives, listen to this carefully, whenever a question gives two different masses of reactants and asks you to identify what is the maximum amount of product you can produce, that is when you need to get alerted and pinch yourself that this question is actually first asking you to identify which one of the reactants is the limiting reactant so that you can correctly predict how much of the maximum product you can produce based on the limiting reactant, okay? I have more analogies to show you. So let me just finish the definition of this and before I show you my analogies. So the one that is not limiting reactant is automatically excess reactant, which is you just use a little bit excess of that. That is, you have more of that quantity. So here is my analogy. Taken directly from the textbook. Let's say somebody decided to do kebabs. So during that kebabs, like say, you pick up skewers, you want to use mushrooms and meat, excuse me. So if you start arranging them alternatively, mushrooms and meat, and for the given amount of meat and mushrooms, if you alternately start arranging them, by 3 skewers, you ran out of mushrooms. So you cannot have more uniformly nicely made kebabs of meat and mushrooms because mushrooms are the limiting reactant. So you can only have 3 perfect skewers. Rest of is just the meat left over with a skewer. So here the mushrooms are your limiting reactants and the meat is the excess reactant. And in a chemical reaction, you always have one a limiting reactant and one an excess reactant, unless you perfectly taken exactly equal quantities. Okay, but we wouldn't do that. That would make it easy, right? But even in, apart from the joke, even in real chemistry work during the labs, the reason that you will have one a limiting reactant, one excess reactant is you would try to look for ratios of these reactants to maximize the amount of you can produce. So to make the maximum amount of product, sometimes you have to use one other reactant in excess. Oftentimes the cheaper one, you use a lot of them if you're hoping to make some of the more of the product than you can normally otherwise would make if you just take them in 1:1 ratio. So that's our chemistry techniques that you don't need to know unless you are going to do research in chemistry. But for now, just learn that in a chemical reaction, there is always a possibility that one of the reactant is a limiting reactant. Okay, don't be naive and expect that both the reactants are going to be of equal moles, equal volume, so you can pick any one of the reactant to predict the product. That would be, I would say, foolish, because it is not the real case. Maybe in very rare cases we would do that, that's a surprise, but almost all the times you have one of the reactant present in limited quantity, another reactant present in excess quantity. So, but we wouldn't tell you, even in the question, no exam going to tell you, and we are just going to give you two different masses. That is when you need to alert and first identify limiting reactant and excess reactant, then based on your calculations on limiting reactant. Okay, let's work on the problems. Let's look at this chemical reaction. So this chemical reaction say that, let's say for the balanced chemical reaction, if you start the reaction with 5 moles of CO and 8 moles of H2, can you identify which one is limiting and which one is excess reactant? Okay, this is a balanced chemical reaction, and you are starting the chemical reaction with 5 moles of CO and 8 moles of H2. What would be the limiting and what would be the excess reactants? So this is how you would identify. You would try to first identify how many moles of the other reactant would be needed if you start with these many moles of CO or H2. Okay, so we are going to first identify, for the given 5 moles of H2, we are going to identify, ideally, if you start with 5 moles of CO, how much of H2 you're going to need to completely react with 5 moles of CO. Let's do that. So if you have 5 moles of CO, okay, how many moles of H2 you need is, using the multimole conversion factor, you happen to need 10 moles of H2. Okay, that's what you have to do. And you have to do the same for the given moles of H2. Using given moles of H2, you try to identify how many moles of CO you need to react with 8 moles of H2. How many moles of CO are necessary to react with 8 moles of H2? If you identify that using multimole conversion factor between CO and H2, you would come to conclusion that you need 4 moles of CO. Okay, so this is where you need to have clear head. So to react with all 5 moles of CO, we said that you need 10 moles of H2. Okay, do you have 10 moles of H2? No. Okay. To react with all 8 moles of H2, you need 4 moles of CO. Do you need 4 moles of, do you have 4 moles of CO? You actually have more than 4 moles of CO. This is what you need to do and compare. So because you actually need 10 moles of H2, but you only have 8 moles, you call the H2 as the limiting reactant between CO and H2, the limiting reactant. And because you need 4 moles of CO, but you actually have 5 moles of CO, you call that as excess reactant. This is how you would identify. You take the available moles and you try to convert into how much of required moles and compare the given number. Okay, look at this information again and again until it makes sense. If you want me to, I can re-explain again. So this reaction wanted to start with 5 moles of CO and 8 moles of H2. Okay, and which one is limiting and which one is excess reactants. There is always a chance that there is one is limiting and one is excess reactant. For that, you need to identify for the given moles of CO how much of H2 you would need. For the given moles of H2, how much of CO you would need. For that, you would use mole to mole conversion factor using 5 moles of H2 CO. We identify that there are 10 moles of H2 is needed, but there are no 10 moles of H2 is provided, which means H2 is the limiting reactant. In other words, and if you just identify one H2 as limiting reactant and other one is automatically excess reactant. And what we are doing here is basically confirming that. So to react with 8 moles of H2, you would need 4 moles of CO, but you actually have 5 moles of CO, which means CO is excess reactant. Again, this is what you have to do in any question that has information about 2 different reactants. If you only give an information about one reactant, that's your lucky day. But if not, that's not your lucky day, because you have to do all of this even before you start trying to identify the product masses or moles. Okay. This is what it would look like. So let's say you start reaction with 5 moles of H2 and 5 moles of CO. There are 5 CO molecules, and these white ones are H2, 8 moles of H2. Once these two started reacting and forming products, you only formed 4 CH3OH molecules because you left 1 CO molecule alone. So this CO is our excess reactant because that is not reacted, it is just left over. And all of the H2 is consumed while one of the reactant is still waiting to react with something. So it is okay sometimes to have excess reactants if it is good for the overall production of the product in a cheap way or in an efficient way. But we just need to know which one is limiting reactant to correctly predict how much of product you're going to produce. Otherwise, your calculations are not going to make sense. So H2 is the limiting reactant and CO is the excess reactant. So now we are going to work on a couple of problems using the same concept. The calculations, I'm not going to lie, looks a little bit confusing. Compartmentalization, maybe one word I can think of to help you, or break it up into small parts, or try to have different titles for different work. But again, don't swing for the fences. Take it in small steps, especially in this chapter. That will help you. Okay. So let's look into the question. So the Alka-Seltzer tablet contains sodium or aspirin and sodium bicarbonate and citric acid. Okay. So when you dissolve it in water, the sodium bicarbonate and citric acid would dissolve in water to form CO2, H2O, and another byproduct there. Okay. So the formation of CO2 causes the trademark frizzling when it dissolved in water. So if the Alka-Seltzer tablet contains 1.7 grams of sodium bicarbonate and 1 gram of citric acid, okay, look for this. The chemical reaction contains sodium bicarbonate and citric acid, right? And the question already gave masses of both of them. This is the classic question where you are required to identify limiting reactants and excess reactants even before you start trying to answer any other parts of the question. And here, clearly, lucky day, clearly asking what you need to do because it is the first problem, okay? So which ingredient is the limiting reactant? What mass of the excess reactant is left over when reaction is complete? One that is not limiting reactant is the excess reactant, and it is asking how much of that is left over. Just like there is 1 CO is left over. And what is the mass of 1 CO? You can identify, right? By converting that 1 mole of CO into mass of grams. That's what part B is asking here. And see what mass of CO2 forms. So what mass of CO2 forms? So to answer C, you need to have an answer for A. What is the limiting reactant? Because the answer for A is responsible for the mass of CO2 formation. Because limiting reactant is the determining factor in predicting how much of maximum amount of product that you can produce. Take it slow. Again, I know some smart guys that easily get it. I'm glad for you guys if you already get it. But traditionally, this topic is been really challenging for majority of the class, at least half or more than half of the class. So I'm going to take it slow and try to knock it out of the park to see if I can make it a little bit better for those guys. Okay. So this is what the plan is going to be. We know that there is 1.7 grams of sodium bicarbonate and 1 gram of citric acid. So what we are going to do is we are first going to identify which one is our limiting reactant by first converting these masses of 1.7 grams and 1 grams of citric acid into moles of citric acid. Okay, so now you have moles of this and moles of this. Then we are going to use the technique, okay? To react with these many moles, how many moles you need? Once you get that number, you can compare for the limiting reactants, okay? First things first, take it in small steps. First, identify amount of moles in both 1.7 grams and 1 gram of citric acid, okay? We got the amount of moles. Now, that is first step, okay? Until so far, it's not complicated because we have done this many times. Converting grams to moles or moles to grams is what you already know, okay? Tricky stuff is what comes next, right? So let's work on problem A. Now, to determine which one is the limiting reactant, pick any one of these, right? Pick any one of these, it doesn't matter. So pick one of these, and apparently this question is, picking sodium bicarbonate. So these are the moles of sodium bicarbonate present in 1.7 grams. Now we're trying to identify, okay, to react with all of the sodium bicarbonate, and usually it helps. I'm not going to make it any more complicated. So pick one of the moles. It doesn't matter if it is sodium bicarbonate or citric acid, right? In this case, it just happened to be sodium bicarbonate. Try to identify how much of citric acid you would ideally need to react with all of these moles of sodium bicarbonate. So in a chemical reaction, they were related to as 1:3 ratio. And once you cancel to each other, you would end up having 0.006745 moles of citric acid. Okay, now this is what you have to do. These are, let me write. Let's see. Given, right? Given or provided, right? Those moles. Now, this is here required. Now compare the required amount of moles to react with sodium bicarbonate, required moles of citric acid to react with sodium bicarbonate moles with the given moles. So compare this number with this number to see if it is smaller or larger. So this number is larger, right? That number is smaller. So based on that, because you need larger number of moles of citric acid than what is given, so the citric acid is your limiting reactant, right? You just compare. So according to sodium bicarbonate moles, you need 0.00675 moles of citric acid, but you only have 0.005205 moles of citric acid. You have less than what is required to react completely with sodium bicarbonate. So citric acid is your limiting reactant. And automatically sodium bicarbonate is going to be your excess reactant. This is the trickiest part. But if you take it slowly, use the techniques to compare, then you will be fine. usually, you will come to the conclusion just by working on any one of the moles conversions. Now, done with the part A, and what is part B saying? Part B is asking us to identify what mass of excess reactant is left over when the reaction is complete. So sodium bicarbonate is the excess reactant. And for that, we need to identify how much of sodium bicarbonate is consumed when the given moles of citric acid is used up. Then see the difference and find out that. So for that, you're going to identify how much of sodium bicarbonate is consumed for the given amount of limiting reactant. So you consumed about 0.0156 moles of sodium bicarbonate. So if you subtract that from the given moles of sodium bicarbonate, you're going to have about 0.00462 moles of sodium bicarbonate. Okay. Once we get that, you're going to convert that sodium bicarbonate into, yeah, this number is not correct. I think in the previous slide it is something like 0.02406 or something, right? Yeah. So you're going to convert that 0.00462 moles into grams of sodium bicarbonate, because this is all used up, but you still have excess, and we're just converting back to the grams of sodium bicarbonate. We used about 0.38 grams of sodium bicarbonate excess. Okay. Now, remember, part C is asking us what is the mass of CO2 is formed. You can only identify mass of CO2 is formed based on the amount of moles of limiting reactant. Now, which one is our limiting reactant? Citric acid is our limiting reactant. So you're going to identify how many moles of CO2 is going to form based on the relationship between given citric acid moles with the balanced equation relationship between citric acid and carbon dioxide. So for the given moles of citric acid, and CO2 and citric acid are related to each other in 3:1 fashion. So you end up going to produce 0.01562 moles of CO2. And when we convert that into grams, that will be about 0.68784 grams. And this is how we do it. And I totally agree when students come, well, I don't know why well, yes, complain, but I don't like that word because we all wanted to learn this one, right? So when students express that this is difficult, I totally agree with them. I don't think we should complain because this is part of the learning for anyone that goes through the general chemistry class, and part of something that we all have to master, at least to complete the general chemistry year. So it is challenging, but with practice, it is doable. For smart guys, they don't need practice, but for rest of them, like me, we all need practice. So we are going to practice, right? That's all. So it's a little bit easier topic, but still we are trying with the limiting reactant again. But here is what you need to do. When we do any labs, if you remember, when you do any labs, at the end of the lab, you usually have to express your answer in percentiles, right? We did that. So percentiles, you would identify by taking the actual yield in a chemical reaction you obtain over theoretical yield that you calculated from the calculations on paper. So theoretical yield is what you expect if 100% of the limiting reactant converted to 100% of the product. Okay, but that's not always the case when you do the lab chemical reaction in a lab. Sometimes you would get, well, most likely you would get less than what is 100% ideally is. So that is called actual yield. And you just want to express how successful that reaction is, or how close to that chemical reaction to is. Is it 100% or less than 100%? This is how you would identify the percent yield, by taking the actual yield over theoretical yield multiplied with the 100%. Okay, we're just going to work on one problem regarding that. Then this topic will be over. So aspirin, or in other words, acetyl salicylic acid, is the most commonly used pain reliever in the world. Okay, it is produced by the reaction of salicylic acid, the one on the left, reactant, and acetic anhydride, the one on the right side, reactant. Okay, so in a certain aspirin synthesis, 104.8 grams of salicylic acid and 110.9 grams of acetic anhydride are combined. Oh, they both are reacted. Calculate the percent yield if 105.6 grams of aspirin are produced. This is a long calculation. It doesn't look like long calculations, but this is because you were given the masses of the both reactants. If at all you were given the masses of the both reactants, you have a job to do. Your first job is to identify where is the limiting reactant. First identify the limiting reactant, then talk about identifying the mass of the product, ideally the theoretical mass of the product, then compare it with the given actual mass according to the question to identify the percentage. So it's a long strategy. So again, because I cannot stress this enough and I don't want you to forget this, right? Whenever you are given masses of both the reactants, do not do anything other than first identifying where the limiting reactant is. Because anything else that you do other than going through correctly identifying limiting reactant is useless. Because your results are going to be incorrect if it is not tied with the limiting reactant. Okay, so how do you identify limiting reactants is you convert the masses of salicylic acid and acetic anhydride into moles of salicylic acid and moles of acetic anhydride, and you compare 1 moles of salicylic acid into how much of acetic anhydride you need and compare those numbers of given and expected. That is when you would identify the everything is here. So this is what you have to do. From the given mass of salicylic acid, identify how many moles of salicylic acid you will produce. From the given mass of acetic anhydride, identify how many moles of acetic anhydride is present. Now identify the limiting reactant. Ratio. Okay, so luckily, if you remember the previous slide, there are no more coefficients in front of the salicylic acid reactant or acetic anhydride, which means they were in 1:1 ratio. This is your lucky day. Because they were already in 1:1 ratio, you don't have to do that extra calculation to compare because there is answer directly looking at us. The one that is present in less number of moles is limiting reactant. The one that is present in more number of moles is going to be our excess reactant because reactants are already in 1:1 ratio. We don't have to do anything else to identify the limiting reactant. So this is going to be our limiting reactant. Now, our goal is to identify what is the theoretical yield of the product, the aspirin, if you start the reaction with a 0.7588 moles of limiting reactant. For that, you would try to identify how many moles of, well, let's go back. I just want to take it slowly for you guys. And for this 1 moles of salicylic acid, which we identified as the limiting reactant, the acetyl salicylic acid aspirin is also happened to be luckily 1:1 ratio. So the salicylic acid is going to be maximum produced is 0.7588 moles, which is what we directly taken, right? So we don't have to, we just saved that calculation step as well. So we are directly converting these moles of salicylic acid, the acetyl salicylic acid, into grams of aspirin. So we happen to theoretically can produce 136.7 grams of aspirin. Now, however, the question asked us to calculate the percent yield if we got only 105.6 grams of aspirin. And how do we do that? We calculate the percent yield by This is the duplicate of previous slide. Okay. So we calculate the percent yield by calculating the percent yield by taking this formula. Question gave us it only produced 104.6, but we identified that theoretically it should be 136.7. So it happened to be that the percent yield is 77.25%. That is the percent yield. That is how you would identify. So that's all about for this topic, and we most likely done with this chapter. And next topic is easy one, and we might even go through that topic during our discussions in the classroom. So get a good notes and try to take good notes and try to look for patterns and break it down into small chunks, and reach me out if you are struggling or freaking out, which is totally expected. And I'm here to help if you're struggling even after these lectures. And again, totally expected to reach out by students to ask me to explain this again multiple times. So if you ask me more times, I'm going to come up with more different ways of explaining it to you until you get it. Okay. So all you need to do is ask me.